Quanrud from Purdue.
Thanks, guys. First, since I have the stage, I just want to say thank you to organizers of this week and the whole. Okay, that seems better. I want to say thank you to this for the organizers of this week and the whole semester for a wonderful program. Okay, so the title of my talk is Quotient Sparsification for some modular functions, and I think in the time allotted, my goal is just to roughly explain each of the terms in the title. So I'll start with stuff we're used to. So graphs, two cuts in graphs, right? So I give you some unweighted graph, maybe a dense graph with some edge weights, right? And as we know, oops, sorry. A cut is just, put some vertices on one side, put some vertices on the other. The edges going across the two sets, that's a cut. Everyone, of course, knows this. Right, here would be another picture of a cut. I really went all out on these pictures. This would be another cut, edges that are between vertices. Don't count on the same side. Okay, so cut values are important, as have been kind of reinforced all semester. They determine the max flow or connectivity, or we hear about expanders all the time, right? These are all functions of cuts. Okay, so in cut sparsification, we're given some kind of input graph, and this is particularly useful when the graph is maybe very dense and maybe there's some redundant information. And the high-level idea is to somehow produce some kind of sparser graph, right? Same vertex set, fewer edges. You're allowed to reweight the edge weights. And we really want the number of edges to be small. We want to compress things. We want the ensuing algorithm to run faster on a smaller input set. And in the case of cut sparsification, I want to preserve the weight of every cut. So if I drop some edges, I'll necessarily have to increase the weight of some other edges to compensate. And so, a very important result in this area, following a line of results, Bengcher and Karger showed that you can start with something close to n squared edges, but you can get it down to n log n over epsilon squared, and guarantee that for any of these cuts, I'll preserve the weight of the cut up to a 1 plus epsilon factor. Okay, so maybe 10% error or something like this for every cut. Right, so it's quite surprising. And now we understand this phenomenon much better. We have, spectral sparsifiers. We can actually get rid of the log n, which is spectacular. There's lots of other perspectives on these cuts. We kind of heard one implicitly this morning as well. Okay, so of recent interest has been generalizing this kind of framework to hypergraphs. So this is my best attempt to draw a hypergraph. It remains open to draw a pleasant hypergraph. But the only difference from before with a regular graph is that a hyperedge can have more than two vertices. So here, if you can barely make out the colors, everything's a triangle having 3 vertices in each edge. Okay. And but otherwise, the definition is the same. I take a set of vertices on one side, and I'm looking at the edges that go across the cut. Edges inside one side, that doesn't count, right? Here's another example, right? Another example, yeah. So, okay, so these are, I guess, cuts of some kind of hypergraph. So hypergraph cut sparsification, we can frame roughly the same problem as before. I give you a really dense hypergraph, and I want to come up with some subgraph, only retain a subset of the edges, and I'm allowed to, again, adjust the edge weights. And just like before, morally, I want to keep the number of edges I retain small as possible, and I want to preserve the weight of every 2 cut in the graph. Okay. And so this has been some recent interest, and there's been a number of results, but a very strong one by Chen Kanagda was sort of able to recover the Bang-Shah-Carter result, which is they can get the number of hyperedges down to n log n over epsilon squared, while preserving the weight of every 2 cut up to 1 plus epsilon multiplicative factor. And there are other results in this space, often incomparable, or more general, or something like this. So there's been sort of spectral analogs sort of inspired by the spectral line of work. You can also sparsify sums of symmetric submodular functions, which also generalizes this. Okay, so what I want to present today is some generalization of this hypergraph cut sparsifier, and really just a certain combinatorial perspective. So I have to unfortunately introduce quite a lot of definitions. But let me start with Matroid. So a Matroid is sort of a combinatorial set system. This is what we call the ground set, just some set of elements. Okay, and script I is the family of feasible sets, also called the independent sets. Okay. And we have just 3 basic governing rules. One is that the empty set always counts as feasible. The second is the hereditary property. So if I have 2 sets S and T is feasible, and S is a subset of T, then S is also feasible. And lastly, maybe most interestingly, if you have 2 feasible sets, any 2 feasible sets, well, one is bigger than the other. So T is bigger than S in cardinality. You can always find an element in T, but not S, that you can add to S and maintain feasibility. This augmentation or exchange property is sometimes called. Okay, so these last 2 properties actually tell you that a maximal independent set, like I just keep trying to add elements while maintaining feasibility, will always be maximum. Okay, so as many of you know, like greedy algorithms tend to be very well behaved in this stuff because of this. So, okay, let's do an example that we're all very familiar with, the graphic Matroid. So these are forests. So, all right, fix some graph, some underlying graph. And the ground set, sort of our elements, will be the edges. Okay, so every element is an edge, not a vertex. And the feasible sets are any edge set that's acyclic or a forest in the graph. Right? So just to check off these properties as we get warmed up, an empty edge set counts as a forest, not a very interesting forest, but still a forest. A subset of a forest is a forest. And as you guys know, if you have 2 forests, but one has strictly more edges than another, then the larger forest, I should be able to find some edge and connect 2 different components of the smaller forest. Okay, and maintain feasibility. Okay, so this we all know. We all know that minimum spanning tree has n-1 edges and stuff like this. Okay. All right, I have a few more terminology. Okay. All right, so let me explain this notion of rank. So the rank of a set S is in general the maximum cardinality of any independent set of S. So you give me a bunch of forests and say, oh, what's the size of the spanning forest of these edges? And we sometimes refer to the rank of a Matroid as the rank of just everything. So for the graphic Matroid, if I have some set of edges S, we'll just, get the maximum forest. So I'm just going to take as many edges as possible without inducing a cycle. And if we kind of just think it through, this is actually going to be n minus number of connected components. Okay, so if it's a connected graph, the maximum cardinality is n-1, which again, just reinforcing what you know. I want to point out 3 properties about rank, because rank is actually just going to be a specific example of something we could work with. So when it's monotone, if I take more elements, I might be able to make the maximum cardinality independent set bigger. The second, and very important, is submodularity. So if I have 2 sets S and T, okay, and I consider like adding the element E to S and I evaluate it, right? Which for rank is saying, oh, am I going to be able to increase the cardinality of a maximum independent set? If S is smaller than T, then then sort of that gain relative to S will always be at least the gain relative to T. Because E might be redundant for T, but not necessarily redundant for S. Okay? Decreasing marginal returns. Last point is a little bit more technical, but to make the bounds work. It's normalized in the sense that any marginal value, I'm adding E to T and evaluating it, it's either 0 or at least 1, right? I'm either adding an element to my base or I'm not. So if you didn't have this property, you'd have to rescale. Okay, another terminology, the span. So for a fixed set S, the span of a set S, the span is going to be the set of elements that don't increase the value. Okay. And a set is closed if it's equal to its own span. So for the graphic Matroid, I have some set of edges S. Okay. And the span is going to be all the edges that are already connected among my set S. So this will not help me increase the size of a forest, the maximum forest. Making progress. We finally got to one term from the title. Okay, so a quotient. A quotient is a complement of a closed set. So Q is a quotient if I look at the complement and it's closed, or I can say, oh, I look at the span of some set that's automatically closed. What's everything else that's not spanned by S? That's a quotient. That was terminology that I picked up in a paper by Carter. So for a graphic Matroid, and I have some set of edges S, as we saw, the span is the edges that are already connected. Okay. So if I remove all those edges, or I look outside, what's left is the edges going across components. Okay. So a quotient is some kind of Matroid language to express a cut in the language we're used to. Okay, so all right, Matroid quotient sparsification. What does that mean? Okay, I give you some Matroid where n is the number of elements and r is the rank of the Matroid. I don't know how to draw a general Matroid, so I just stuck with a graph. And the goal is just trying to pattern match after graphs, trying to reduce the number of elements, but trying to preserve the weight of every quotient, which we saw generalizes a cut. Okay. So for this then, this is what we're able to get. We're able to get, the number of elements I take or the support of the weight, however you want to look at it, is going to be proportional to the rank of the Matroid, log n over epsilon squared. Okay. And it's going to preserve the weight of every quotient up to this error parameter. Okay, so if you want 10% error, this will become 100 times r log n. Okay. And you can do it fast and things like this, but that's okay. All right. I want to take this and just project it back onto the stuff we're used to. So let's look again at the graphic Matroid where, again, the independent sets are forests. So again, they have this span and the quotients are the edges being cut, right? So preserving quotients, we're preserving cuts. And I just want to plug in these parameters. So for this r log n, where r is the rank, that will map to n log n in the graph where n is the number of vertices. So sorry, it's a mix-up of notation. But if as we're kind of used to in graph language, n is the number of vertices, that gives the rank of the Matroid. Really, n minus 1 is the rank of the graphic Matroid. So you'll get n log n over epsilon squared edges like we were hoping and expecting. And then this is saying, again, we approximate all the cuts. So it matches the Banksia-Karger guarantee. Okay, so I want to try to generalize this a little bit more. Okay, and I'll give an example as well. So we talked about, the rank function had these three properties before. It was monotone, submodular, and normalized. Okay, and for general f, not just rank functions, we can have the same notions as before. I can define like the span of a set as the elements that don't increase the value. I can have closed sets if it's equal to its own span. And a quotient is the complement of a closed set. Okay, so we just take rank, we plug in f, same definitions. And then the rank of this function will be the overall value of the whole thing, f of the ground set. Okay, so for hypergraphs, we can look at this function. F of a set of edges, S, is n minus the number of connected components of S. So, two vertices are connected, they're in the same edge, or, there's a bunch of edges you can hop across. Okay. You can imagine taking a hyperedge and replacing all the regular undirected edges and looking at those connected components in the regular graph. So, the span of some set of hyperedges is, again, the set of hyperedges where all the endpoints are already connected by your set. And then the quotient then will be the edges that are going across connected components. And again, actually, the rank is n minus 1 if G is connected. Okay, so, right, so here then, a quotient might look like this. So if purple is S, then the remaining colored edges are going across the components induced by purple. There's one kind of interesting thing, is that the quotients directly map to k-cuts. I break the graph into k components, and I look at the hyperedges going across it. Okay. But what's kind of odd, so k-cuts, of course, include 2 cuts where I just split the graph in half. But unlike graphs, in a graph, if you preserve all the 2 cuts, then the k-cut is going to be like the sum of all the 2 cuts divided by 2 because you're just double counting edges. So if you preserve 2 cuts, you preserve k-cuts. But that's not true for hypergraphs. An edge can appear in 3 or 4 or 5 components. So that's sort of something unusual about hypergraphs. And right, so submodular quotient sparsification, I'm using hypergraphs as an example. I again want to just decrease the number of elements and preserve the weight of all the quotients of this fixed submodular function. And letting R be this kind of thing like a rank, we get that the support is R log Rn over epsilon squared. Okay, and then we're able to preserve all the quotients up to a 1 plus epsilon factor. Okay, so generalizing the previous slide. Right. There's some algorithmic stuff. So let's look at hypergraphs. I guess the distinction I'm making here is now we're going to try to preserve all the k-cuts in addition to the 2 cuts. If I have a hypergraph, I want to get a smaller number of edges and preserve the weight of every k-cut. And plugging in those parameters from before, you'll get n log n over epsilon squared hyperedges and preserve the weight of every k-cut in addition to the 2 cuts. And you can do it. Okay. I'm going to give a couple more examples just for fun because, what else could be modeled by some modular function or this framework? So let's look at actually vector spaces. Okay, so we have some vector space X. This is linear algebra terminology, not the Matroid terminology, although it will coincide at some level. But you have some overall vector space X, like Rn or something, and you have some subspace Y, and then the kind of complementary subspace, or X sub minus Y, is called the quotient space. Okay. So okay, here's then what we're going to get. Let's say you have n vectors and you have some weights on the vectors. Okay. We can find a subset of vectors where the number of vectors is proportional to the dimension of X. So if X is d-dimensional, you'll get d log n over epsilon squared vectors. And you'll preserve the weight of every one of these quotient spaces. Does anyone want to guess why? I guess I'm usually doesn't accurate. Okay, so there's something called the linear Matroid, which actually inspires a lot of the terminology. But we take ground set all the vectors. And the independent sets are, in the linear algebraic sense, the independent sets of vectors. And the Matroid quotients of the linear Matroid are going to map to these quotient subspaces. All right, so that's fun. Oh,
Does that case follow from anything before, or is it new, like the linear case?
to my knowledge, it's new, and I even bounced it off Arun to see if we could recover it other ways, and we weren't able to find other ways.
Yeah, thank you. Couldn't tell.
I also never imagined this until, I mean, in hindsight, we're like, oh, what's a Matroid? And looking around. Okay. Here's another example that's kind of fun. Take coverage. Okay, so you have elements and sets. Okay, and the elements are weighted. And what I want to do is subsample these elements and preserve the weight of every union of sets so that I can just run coverage or something on a smaller set of stuff. So, okay, the theorem is that we can take our elements and get it down to a number of elements proportional to a number of sets. Okay, so in some overdetermined case, you have way more points than sets. And you can preserve the weight of every union up to a 1 plus epsilon factor. Okay, so it's a little notation heavy, but this is the weight of some union of sets. And this is the reweighted union intersected with our subsample. Okay, so this is, yeah, I won't do the thing like before. But one thing kind of fun is, one way to see this, well, one way is you can reduce the hypergraphs, but another way is you can look at this hitting set function where for a set of points, I look at the family of sets that cover at least one point, and out comes the quotients. Right? Because I got it backwards. I originally thought, oh, coverage is submodular, so it'll be a function of the sets, but actually it's the hitting set of the points. Okay, so for lack of time, I'm going to skip kind of most of the technical parts, but I have full slides with a little more. But at a high level, if I had more time, I would talk about precedents from Karger's algorithm. So Karger had already, looked, for example, in the first step, he's showing how to preserve the minimum cut in the graph. And this is followed up by Bengcha and Karger, who show how to preserve all the cuts in a graph. But a third important precedent also connected to Karger. So here's sort of papers that I think many of us are familiar with in graphs. I'll skip this. Skip this as well. Oh no, let me. A third paper I want to mention by Karger is he sort of started to do to Matroids what he had been doing to graphs. So he had studied a random contraction algorithm in Matroids where you take an element and you kind of look in the remaining quotient. Okay. And in some ways sort of did the analog of preserving the minimum cut. He's trying to preserve the minimum quotient in a Matroid. So going into this, we sort of had this, you can preserve the minimum cut, you can preserve all cuts, and you can preserve the minimum quotient. So just for lack of time, I just kind of labeled these. And it doesn't matter too much. We put some effort into kind of decomposing a Matroid and doing some things inspired by Bengcha Karger. But morally, we're sort of occupying this bottom right square where, okay, we can preserve all cuts, we can preserve the minimum quotient. Now we're trying to preserve all the quotients. I should maybe say one word about optimization. To this end, I'll only make a pointer to, in order to try to do things fast, if you wanted to do something in nearly linear time, we found this kind of general push-relabel framework of Frank and Miklos to be very useful. That's all I wanted to say. Okay, and then I'll just conclude then, sort of more informal conclusion. So, there's lots of interest in kind of spectral or more algebraic notions of sparsifiers. So can you capture this generality, along those lines? And an important point is, k-cuts? Can you do k-cuts in a hypergraph? Because we're kind of used to, if you're trying to model things as a vector, I put everything on one side as -1, everything on the other side is 1, right? It's on a line or something. But with k, it's not even clear where to start. Okay, there's some general theorem, some general sparsification. Maybe there's some fun opportunities out there, surprising things we can sparsify that we didn't think of. I mean, examples I gave was just like, oh, what's submodular, and working through them and learning stuff. But maybe if we keep this in the back of our mind, we'll find something new. I didn't talk about this too much, but in order to do things fast in graphs and hypergraphs, we did certain decompositions of the graph and hypergraph very fast. It's roughly along the Tutt-Nash-Williams kind of tree packing and doing it recursively very fast. And just wondering, oh, could this be useful for some other context besides? It's used to sort of figure out the right sampling probabilities when you decompose the graph, and maybe there's other situations. All right, thank you.
Any questions for him?
I think the hypergraph, like span tree, is not a Matroid, and I noticed you use the term polymatroid. Can you explain it a little bit?
Yeah. There do exist other ways, like Lovatz is associated with a different Matroid point of view. I'm sorry, this will take a while. But so in short, the rank function of a graph is just it's a rank function for hypergraphs. So here, n minus number of connected components start with an empty graph, right? And I have a hyperedge with 10 vertices. So immediately this goes down by 10. It's not going down by 1 like you would want for a rank function, but you still have monotone and you have some modularity. So I guess maybe this was part of the motivation for the generalization. And maybe the best example I have of maybe why moving to greater generality is useful. But what's important is that as you add hyperedges to your graph and you connect more things, each other hyperedge is connecting less, right? Because some of its endpoints are already connected. So as long as that marginal contribution is going down, then you'll be okay. I'm not sure if this answers your question very well.
Yeah, is the log n loss necessary in some of these?
Is a log, okay, the question is the log n loss necessary in some of these? Well, I'll see, okay, so the question is log n necessary? It's a log r log n. So something like this. So I guess I don't 100% know, in the sense that we do for spectral have these stronger bounds. That said, within at least this line of argument, removing the log n might also roughly imply improving a log n from like the Bank-Jakarta approach, which I'm sure we've all kind of tried once before. And when we're counting quotients, there's some n to the something, because the more elements you have, the more quotients you can have. So those are just two technical obstacles. That's not a necessary thing. Those are two things I'll cover.
Any other questions? Great, let's then consider